Welcome back. In this session we're going to learn how to use interp1, interp2, interp3 and interpn to perform interpolation for the one-dimensional, two-dimensional, three-dimensional and generally n-dimensional data. And they're very similar, and we'll start with the interp1 first. Interp1, which is called in this order, interp1 receives some value x and some values y, and then some value of x prime, for example, to evaluate the model in these points, and that's a modeling and evaluating function. And this will return y prime, which are related to these values using the model which is found based on the provided data points. And for interp2, we have x, y, and z. X and y are input, z is our output, and these are our data points. And we provide some x prime and y prime, and then this will give us the z prime, which is the value of the model which is created based on provided data and evaluated on x prime and y prime data points. And interp3 is almost the same, x, y, z, and v, and these are our data points, and we'll give the function x prime, y prime, and z prime, and that will calculate v prime, the value of function evaluated at these points, which is created based on these data points. And for interpn, we generally provide some inputs, some value, and some evaluation points. And always, for example, we have n inputs here, one output here, and n sample inputs here, and this will give us the value of output for these data points. And you see they're very similar. And by calling the interp1, we will get the value of model on these, and this will not give us the structure of model. Let's do an example, and for example, let's define the function, let's define a data point, a set of data points in an M file, and clc clear close all, and let's define the function, for example, 1, 2, 4, and 5, and y equals to 2, 2, 3, and 1. And let's define xx as some points from 1 to 5, 100 points here, and let's calculate yy as interp1 of these set of inputs, these set of outputs evaluated at these points. And that will give us the solution. Let's save the program and run it, and you see yy and xx are same. Let's plot this solution figure, plot x, y as some are red colored O markers. Let's hold down and let's plot the xx and yy blue colored, and let's show the legend as data points and fitted model, and that's it. It fitted a linear model between any two consecutive data points. And if you provide, for example, 0 to 6, some data points out of the initial data points, you may not get the output. And if you see yy, that's some nan, not a number of values here, and that's because of the extrapolation behavior of interp1. Let's return back to 1 to 5, and if you see the help for interp1, you see that fourth parameter is the method and the fifth parameter is the extrapolation strategy. Let's see what are the values available for method. These are linear, which is the default, nearest, and that's the nearest neighbor, and next, previous, p chip, cubic, v5 cubic, and that's almost absolute, and Makima and spline, and the default is linear. And let's write down these names in our slides. So the available methods are linear, which will give us a linear model between any two of data points, linear, nearest, next, previous, and p chip, and cubic, which is same as p chip, and v5 cubic we don't discuss it, and Makima, which is a modified Makima cubic method, and spline. Let's, for example, use the spline method and see what we get. And if you use a spline, you get a smooth model. And if you provide some points outside of input values, you get the extrapolation behavior here. And if you provide, for example, nearest, and you see does not extrapolate, and to extrapolate, xtrap will extrapolate the results. And if you, for example, use the next, every data point will be every point between two data points will use the value for the next data point. So this jumps out here and this jumps down here. And if you use previous, the result will be changed. And for the nearest, that will somehow in the middle. So in these points, this is the closer to this point than this one, and this is closer to this point than this one. And for example, if you use cubic method, you'll get this, and this is a piecewise cubic polynomial model. And you may use, for example, spline model here. And that's a interpolation method, which gives us the value of the model on some specific points. And for high dimensional data, you can use interp tool in a very similar approach, and for the 3-dimensional and n-dimensional in general. However, the p-chip is not available for higher dimensionals than 1-dimensional, and also the Makima, I think, that's not available. And so the next and previous are not defined for the higher dimensions. So we can use linear, nearest, cubic, and spline methods, and that's enough to our modeling purpose. And let's do some examples, for example, for 3-dimensional data, 2 inputs and 1 output. So, for example, you may create a mesh grid, for example, from -5 to 5, and let's name the values as x and y. And if you do this, you will get these data points 11 by 11. And if you evaluate the z, for example, peaks x and y, and if you plot these values, figure, and for example, surf of x, y, and z, that's our data points. You can see this from various angles and point of views. And we have here num.el x 121 data points in 3-dimensional space, and we're going to fit a model on these data points. So let's create some data points to evaluate the model. XX and YY are mesh grid of this -5 to 5, but this time with a spacing of half, for example, and that will give us more points, 4 times more than the original data points. And let's find the ZZ. which are the outputs of our interp2 model, which is built upon y, x, y, z, and evaluated at x, x, and y, y. And if you do this, you'll get xx, which contains 441 data points, and xx, yy, and zz are same. And now let's subplot one row, two columns in the first area, and let's add some title here, original data, and model output here, and in second area let's have some spaces here and use xx, yy, and zz here, and let's run. That's it. That's the model which contains 4 times more points, and it's almost correct. However, if you change the modeling approach, for example for cubic, you will get some smooth models, and you see that it's smooth. Or for example, use spline here, you'll get some more smooth models. And if you provide some more data points, you'll get a pretty smooth model of the same data. You'll get some smooth model from same data here, and these fluctuations and noises are due to the modeling errors. And you may compare the original output to the model output by plotting another surf in another subplot. And I'm going to left it to plot a surface of the original data points, which is calling the peaks function on xx and yy and plotting the output. So that's it. For interp3 and interpn, that's almost the same, and you can use interp for perfect modeling and fitting in higher dimensions as well.